Alright, good morning. Now this is the video recording of a revision lecture on topic 5, Synchronous Generator. Now synchronous generator is an AC topic. It's an AC topic, right? And it is a very short topic, as short as the step motto topic. So I would say it is not easy to understand, but should be able to do it nicely if you know the few formulas that's involved in synchronous generator. Now, generator, as it says, is about generating electricity. So, according to law of electromagnetism, it's still the same. Right? How to produce electricity? You have magnetic flux, right? React with motion. That gives you electricity. But in this case here, synchronous generator instead of producing DC electricity, is producing AC, AC source. Now, in Singapore, you do not see waterfall, the big waterfall. But in big countries like United States, China, this country, they have very big waterfalls. And I believe you have learned in your O-level physics that how waterfall is being used to generate electricity, right? The waterfall is high up in the mountain there, and when the water gushes down, that is converting potential energy to kinetic energy, and then we have a turbine below to be turned by the waterfall, and that is motion, right? And then if you have magnetic field around it, so magnetic field react with the motion, that will produce electricity, right? So that's one way. Now in Singapore, as I say, we don't see many waterfalls, but what we can do is actually we buy petroleum, right, or gas, and then we boil water. And the water when it's being boiled, steam is being produced, and as the steam rises, we turn the turbine on top, right, and then we have magnet. So this steam turns the turbine that reacts with the magnetic flux and produce electricity, right? So these are the two ways of generator to generate electricity from waterfall as well as steam turbine. Now that describes to us that there are two types of synchronous generator. They are the salient pole type, and the cylindrical rototype. Now, if you refer to the notes, it describes to you what are the differences between the two. Now, salient pole type are usually driven by hydro turbine, nervous by waterfall, right? And because it's by waterfall, so it's low speed operation, and it is not suitable for high speed operation because the waterfall is high magnetic impact, forces impact on the rotor, right? So it can be quite damaging if it's on high speed, right? So it's on low speed. And that is a salient pole type, right? Whereas for cylindrical rotor type, is driven by steam turbine and can therefore take high speed. Okay, and it has small diameters, and this one can have large diameters. Okay, with that, let us now go through the some formulas involved in this topic. Right, now the first one, there are only 5 learning points if you were to refer to your notes on synchronous generators. Okay, the first one is frequency is equal to Ns multiply P divided by 120. Of course, that is Hertz. Right, in Singapore, our frequency is usually 50 Hertz, right? So the generator, the electricity that is being generated, what is the frequency of the AC? The formula is Ns times P over 120. Now Ns is the speed, okay? Ns is the speed, right? And P is the number of poles on the rotor, right? Secondly, we have the EG generator. Is the phase voltage generator is equal to 4.44 Fn flux. Now, you may have seen this formula before. If you recall, in our transformer topic, we actually use this formula. right? In generator also the same. You can therefore use this formula to find out what's the voltage produced per phase, which is equal to 4.44 multiplied by the frequency, and the n is actually the effective number of turns, and multiplied by the flux. Now the only thing that is different is this turn. Now in transformer, if you were to say it's 1400 turn, you just plug in 1004. But in synchronous generator, we say it's called effective number of turns. Alright, so if the factor is therefore is equal to 0.9, for example, alright, 0.9, and the number of turn is 1400 turn, then you cannot just use 1004. You must multiply by 0.9. Must use the winding factor. Right? So that is how to calculate the frequency of the generator AC voltage, and how to calculate the voltage per phase using this physics formula if you know the flux. Alright, 3. The equivalent circuit of a single phase generator. We just want to draw one phase. So this is the one phase. Okay, one phase. This is called the synchronous reactance. And this is the load. And this is the terminal voltage. And this is the voltage generated per phase. And here is the magnetic flux. Okay, magnetic flux, and this is the field current. So Kirchhoff's voltage law say the voltage generated per phase is equal to the current. This is the current per phase, right? Ohm's law says this voltage plus this voltage. So it's therefore JIPH multiply JXS plus the terminal voltage. Kirchhoff's voltage law. Okay, so if you know the current, if you know the value of the reactance, and why do we put a J? Because it's inductance. Plus the terminal voltage. So this is the third point, and the fourth point is the synchronous reactance. How do we calculate the synchronous reactance? Now, just like transformer, we could do an open circuit test and short circuit test. Likewise, for synchronous reactance, if you were to do the generator, if you were to do an open circuit test and short circuit test and obtain the open circuit voltage and the short circuit current, using the two values by Ohm's law, you could actually, using the open circuit voltage per phase divided by the short circuit currents per phase. Alright? Ohm's law will give you the synchronous reactance. Okay? And last point is the voltage regulation. Voltage regulation of a synchronous generator is the no load voltage minus the full load voltage divided by full load voltage. Right? Now, as just like in transformer we have voltage regulation, synchronous generator also have a voltage regulation. This is a measurement of how good the generator is. Right? That means to say, let's say it is 5 kV when it is no load. But when it's full load, the voltage drops to 4.8 kV. Then the voltage regulation says 5 kV minus 4.8 kV divided by 4.8 kV. Yeah? So these are all the 5 learning points for the synchronous generator. Okay? Let us now carry on with how to make use of this learning point to do questions. Right? The first one was F is equal to Ns multiply P over 120. Right? Now, so for example, if I were to refer to the tutorial questions, right? If the motor turns at 300 RPM, okay, and it has a frequency of 50 Hz, right? Then you ask, hey, how many poles is that? Right? So of course, in this case here, we see that we need to use this equation, right? So substitute the value here, 50 Hz equal to the speed multiplied by P by 120, right? So therefore, P can be calculated. That's how we make use of this formula. Formula number 1. Alright, number 2, how do we use the formula of EG per phase is equal to 4.44 Fn flux, right? You do recall what we say about the number of turns here. We have to multiply by the winding factors. That means how many percent of the winding is effective. Okay, so let us see these questions. Yeah. Now it says here. Let me find a question. Okay, now mine. Let me see. The frequency is equal to 50 Hertz, right? And the number of turns is equal to 2,600 with winding factor of 0.84, right? And the flux is equal to say 25 Weber, right? Then for you to calculate the voltage generated per phase, we'll plug in the formula, which is equal to 4.44 multiply 50 multiply 2006 multiply 0.84. You must multiply by the winding factor, yeah, and then the flux 25. So that is voltage. Okay. Now, then what if I ask you for the generator voltage, line voltage? If it is a star-connected circuit, phase voltage, how to convert phase to star to line voltage? You have to multiply by square root 3. Yeah, so that is how we use the second formula. Alright, the third one was about the circuit. Remember the circuit? Right, so this is EG per phase, and this is phase current, and this is JXS, and this is the terminal voltage, and this is the load. Alright? Okay, let's find a question that's of this nature. Okay, so say for example in this question here it says there is a 2005 kVA transformer synchronous generator with 6,600 volt, 50 Hertz, 3-phase generator with synchronous reactance which is equal to 1.4 ohm per phase. Alright? The armature resistance is neglected. In other words, actually there is a resistance but it's negligible. And find the generated EMF per phase when it's delivering at full load at 0.8 power factor lagging. Right? So if we were to look at the information here, remember we learned how to use Kirchhoff's voltage law to get EG, right? So we will say that EG is equal to IPH multiply JXS plus the terminal voltage. There's a complication that comes in here. Your calculation here is single phase. But information given here is actually three phase, right? Okay, so now in order to get current, remember what is this? This is apparent power, right? And what is this? This is the voltage, the line voltage. And if you still recall, S is equal to V times I, right? V times I. This formula is single phase. And the information is given three phase. So you have to say it's equal to square root 3 VI. S is equal to square root 3 VI. Right? So I have 2500 kVA equal to square root 3 multiply 6600 multiply current. Right? So therefore, my current is out. When you say current means line current, line current. Okay, line current, right? Current is out. But do you know that line current is the same as phase current in a star connected circuit? Yeah, this question is star connected circuit. So phase current is therefore equal to my line current. Okay, I know the information from here. Now, can I get the angle? Yes, because it's 0.8 power factor lagging. So I therefore is this value and then negative cosine inverse 0.8. Alright, so I have my phase current in polar form already. So with that now, I'm moving on to find my voltage, EG per phase. Now then ask yourself, what's the terminal voltage? Terminal voltage is actually given to you also. Here is 6600. 6600 is actually the output voltage. Yeah, output voltage. So you have to, terminal voltage is equal to your line voltage divided by square root 3. Square root 3. So it's a 6600 divided by square root 3. Okay, so that is a complication when it comes to AC topic with 3 phase and 1 phase. Be careful of your conversion, 3 phase and 1 phase. So with that now, I'm able to calculate EG per phase is equal to IPH negative cosine inverse 0.85. Alright, multiply by JXS, which is 1.4 plus 6600 square root 3, which I make it 0 degree. 0 degree as my reference. So with that, the numbers will come out. And that's how you do, how you make use of this formula, Kirchhoff's voltage law, to find a voltage per phase. Alright? Sounds a little bit complicated. Let's go through one more time. First, you must have the circuit in mind. It's a single phase circuit with a synchronous reactance. Synchronous reactance. Then Kirchhoff's voltage law say EG is equal to this voltage plus this voltage. Now, information given in the question is always a 3-phase information. We are given 250 kVA is actually a 3-phase apparent power. 3-phase apparent power. Yeah? And the voltage given is a 3-phase line voltage. Right? So with that, let me say EG equal to current, Ohm's law, multiplied by reactance plus the terminal voltage. Then ask yourself, how do I get the information? I can find the current using the apparent power. Apparent power is equal to square root 3 VLI. This is for 3-phase. 3-phase. Okay? Right, so with that, 250K equals square root 3, 6600 times IL. I get IL. IL is the same as I phase because it's a star connected circuit. And I find the angle using the power factor. Then plug in to find my terminal voltage per phase. So I divide by square root 3 because it's a star connected circuit. Then I plug the value into the Kirchhoff's voltage law to find the voltage generated per phase. Got it? Okay. Right. Then point number 4 was about XS is how to find using VOC per phase divided by I short circuit per phase. Right? Right. So example, if you are given, see whether I have the question here. Alright, no. Okay, so you see for example, I say my open circuit voltage line, right, is equal to 400 volts. Okay, and the short circuit current line is equal to 25 ampere, 250 ampere, right? Then how do you calculate the synchronous reactance? Synchronous reactance per phase, that's one phase, will be equal to phase voltage. It's a star connected circuit. So how do you convert this into phase voltage? Divide by square root 3. Okay. How about current? It should be the same. Phase current and line current is the same. Alright. So that is your synchronous reactance value. Okay. So that's point number 4. Last point, voltage regulation. Okay. Voltage regulation is the voltage with no load minus full load divided by the full load value. Right? So if you are given that this is a 2600 volt synchronous generator, and when it is at no load, that is the value. When it is at full load, the value is 2560 volt, right? And the voltage regulation is equal to 2600 minus 2560 divided by 2560 times 100%. Right? So that is voltage regulation. And that wraps up the 5 points in synchronous generator that we want you to learn. Just to remember, it's a very short topic, quite straightforward, just like step motto. But the only complication that comes in this topic is that it's a 3-phase topic. So do remember your square root 3 related formulas, like S is equal to square root 3 VLIL, and how to calculate the phase voltage is VL divided by square root 3. Line voltage and phase voltage is the same for the star connected circuit. Alright, that's all.